Okay, so let's revisit the example we had before where we have this sphere and we're exposing it to some generation that's a function of time. The generation varies as a function of time. So first, we start off at t equals less than 0. The whole thing's kind of at rest with the surroundings. Then we introduce this really high generation that tails off as a function of time. So we decided that this is a lump capacitance problem. And the volumetric generation is given here, right? So this is our function that we're then trying to enforce. So we can't really solve this with separation as easily with separation of variables as we could with Laplace. Let's see, so let's go through and do the Laplace solution here. So the first thing let's do is let's convince ourselves that this is in fact a lump capacitance problem, just to refresh ourselves on how to do that. So the Biot number is our conduction divided by our surroundings, which is convection in this case. Okay, so our conduction is going to be L conduction divided by KAC, and our convection is H bar AS. Okay, so then the conduction length, let's use that relationship of the volume over the surface area. So we have volume over surface area times, let's see, AC. Yep. So we're going to use the same surface area as the conduction area, right? AC is equal to AS for this relationship where we're taking volume over surface area. So we end up with that in the denominator times K times, again, H bar AS over 1. So this gives us volume times H bar over AS times K, which if you calculate it for this problem gives us 0.04. Right. So is it, yeah, it's much less than 1, and it's in fact less than 0.1. So this is a pretty good justification that this is a lump capacitance problem. All right, let's also calculate the time constant. So tau is going to be C times R convection. If you do that for this, it ends up being rho times volume times C divided by H bar AS. And that gives us 1.5 seconds. Okay, so we characterize that, yeah, this is a lump capacitance, and about how long it takes to respond is about 1.5 seconds. And note the time scale for this generation, most of it's happening in that first few seconds. So it's pretty important to get an actual model of this because the time constant's on the order of what's happening in the problem. Okay. So let's look here at just how this plots out, just kind of conceptual understanding again. So up in the right-hand corner, we have the actual solution. This is something we did before with the numerical method. So we have the actual solution at for 1.5 second time constant. And then, if we wanted to really understand how this thing behaved, we could try out different properties and look at the responses. So if we had a time constant of 0.15 here, it would follow much more closely. If it was 15 seconds, it would really lag behind, right? So they're kind of just reinforcing our understanding of what's happening in this problem. Okay, so let's actually get to the Laplace part of this. Okay, so to solve this using Laplace, we always have to go through the process of deriving the ODE ourselves, right? That's always on you. You always have to do that part. So let's start with our energy balance here. We say we have generation occurring within this volume. We have an energy storage term because it's not constant as a function of time. And then we're losing heat to the surroundings here. And again, we can draw the control volume around the whole thing because we decided it's lump capacitance. Okay, so let's write out the energy balance here. It is nothing coming in. Okay, so generated is equal to what's leaving, Q dot convection, plus what's stored, which is du dt. Okay, sorry, I'm a little more up there. Okay, so for generation, the generation is actually what, volume times the specific generation, max times exponential of minus t over alpha. I think that was the equation that we had for volumetric generation here. Okay, and then convection, so that was G dot. So convection, Q dot convection is equal to H bar times AS times T minus T infinity. T is a function of time. And then du dt is rho volume specific heat, dt d time. Okay. So this is a lump capacitance problem. We have ODEs and we have all of our energy terms. So now we add this up back together and we end up with volume times G dot triple prime exponential of minus T over A. What do they call it? A or alpha? Yeah, let's call it A. T over A is equal to H bar AS T minus T infinity plus rho V C dt d time. Okay. Go through and simplify this a little bit. So let's divide out to get the highest order term kind of clean. So we end up with dt d time plus temperature over the lump time capacitance, lump capacitance time constant tau LC. And that's equal to T infinity over tau LC plus generation over rho C times exponential of minus T over A. Okay. So that's our ODE for this problem. We've derived that ourselves. Always have to do that. And then the initial condition here is temperature at time equals 0 is equal to T infinity. Okay, so that's our statement of the problem. Okay, so now we have to go through the Laplace steps. Okay, so we have this ODE. Our next job to use the Laplace method is to take each of these terms and transform them into the S domain. Okay. So let's do that down here. Here's the solution we just had. Should be the same. So let's take this solution up here, right? And we're going to do a Laplace transform on the whole thing. Okay, which means actually let's just do Laplace on each individual term. So let's do these one by one. Let's start off with dt d time. So what's the Laplace transform of dt d time? So let's look over, where would that be? That would be right here, right? This guy. It's a little hard to see, but we're using that transform or that property. So that gives us S times now T hat, right? T hat, which is a function of S, minus T at time equals 0. Okay, so that's applying this one here, this guy here, to that, that particular term. So we have one more kind of job to do to finish this. We need to decide what T at time equals 0 is. Well, that happens to be our initial condition, right? So actually what we have here is S T hat. I'm just going to drop the function of S there, minus T infinity. Okay, now sort of notice what we just did, right? We just did this transform. We took a ODE down to just a linear equation, but we also enforced our time initial condition in that process. So when you get to the end of this process, we're going to have to enforce boundary conditions in the S domain. That time should not appear in the boundary conditions because we've already enforced it. We just enforced it right now, right? That's what we just did. Okay, so we've done that. Let's keep going. The second term is T over tau. So Laplace of that is going to be, if you go over, that would be what, number 2 here, this one. So that gives us 1 over tau, T hat. Okay, and then the third term is T infinity divided by tau. That gives us just T infinity divided by tau S, because T infinity and tau are constants. Okay, and then what's this last term is G dot triple prime max over rho C exponential of minus T over A. So the Laplace of that, right, we just have what, a constant, G dot triple prime max over rho C, a constant times an exponential of something. Okay, so if we go back and look, that corresponds to what up here, table 2 right here, right? This guy here. So let's do that, and that gives us G dot triple prime max over rho C S plus 1 over A. Right, so that's our transform. So then the transform for the whole thing, if we bring it all back together, is just the sum of all of these terms, right? It's this term plus this term plus this term plus this term, right? Or these two equals the second one. So we're just adding it all back together according to how the equation's formulated up there. Okay. So let's see. Let's keep going a little bit. So we now have this expression in S. This is great, but how do we actually take the inverse of this? We have to get this back into the time domain. So in order to do that, we need to kind of break it up a little bit. So let's solve this for T of S first of all. Right? We have T of S appearing here. We have T of S appearing here. We want some single expression as a function of S. So if we do that, it's pretty straightforward. In this case, we can just pull out what T hat times what S plus 1 over tau is equal to T infinity over tau S plus G dot triple prime max over rho C S, S plus 1 over A in the denominator, and then that plus T infinity. Okay, so then we can divide through by the stuff multiplying T hat here. Right, this. So we divide that through, and then we end up with everything over here divided by S plus 1 over tau. Right. So now we have an expression. We've actually just solved our equation for temperature in the S domain. Right. So it's a little bit, you can see how it's easier to do that than it would have been in the time domain. Right. We actually only have to solve it algebraically in this case. Okay, so now we need to figure out how to get this back into the time domain. So we have to go through this process of figuring out how to break this up into multiple terms and then do the inverse of each term individually. So let me just write out, if we say, take this one more step, looks like this. So T hat looks like the following: T infinity over tau S plus 1 over tau plus the second term becomes G dot triple prime max over this whole thing, which is rho C S plus 1 over A times S plus 1 over tau. And then the last term is T infinity divided by S plus 1 over tau. Okay, so that's just rearranging from second step to third step. So now you can kind of see how, what we just talked about with separating out the denominator and kind of doing each one individually, how this is going to work. So you have basically 3 terms. We're going to have to treat each of the 3 terms separately and then figure out how to invert or break each term up and then invert each sub part of each term. Right? So starting here with, we'll maybe do one quick example and then I'll wrap it up. So let's start here with this one. Right, this one's actually really easy if you look at the table. It just is T infinity times exponential of minus T over tau. Okay, so that's this term. The first term here and the second term here, I think, are a little bit more involved, so we'll leave those for next time. Okay.